Let's design an AI chat system like ChatGPT from scratch. This type of system is very common and shows up for senior and staff level interviews, especially if you're interviewing at AI companies, because it tests the exact skills that separates mid-level candidates from seniors. And designing this is not just calling the LLM API and then storing the messages to the database, especially if you consider the actual scale that ChatGPT has currently, which is 800 million weekly active users. And these users are sending 2.5 billion prompts every day on average, with 20 million of them being concurrent connections at the peak time. And this chart is also taken from the official OpenAI post from January 2026, where you can see that as of July 2025, they already had 700 million weekly active users, and currently they already surpassed 800 million weekly active users. So we're going to design this complete architecture from scratch, starting from the requirements and capacity planning for the 200 million daily active users. Then we'll cover how we'll be streaming responses to the front end and rendering it word by word on the client side by using servers and events. Then we'll cover backend microservices architecture and how that looks like for a system at this scale. We'll also cover a controversial database choice that OpenAI made, which is they are not sharding the database, even if they already achieved 800 million active users weekly. And this might challenge what you already know about database sharding, but you can see how they went with a simpler approach and they decided to not complicate it even at this stage when they already surpassed millions of users. Then we'll cover the multi-region deployment across 6 regions for high availability. We will even estimate the infrastructure costs, and you will see how much this actually costs to run this whole infrastructure like ChatGPT on the cloud. And at the end, we'll also design for high availability for 99.9% and less than 2-second latency, consistency, and we'll also scale this to 1 billion weekly active users at the end. But let's start from the very first step, which is clarifying the requirements and then estimating the capacity and storage that we will need for the system. Before touching any code or drawing diagrams, let's first understand what we are building and lock in the scope, because there are many functionalities when it comes to systems like ChatGPT or cloud, and we of course won't be able to design all of that in a short 1 hour or 2 hour session. So we need to clarify what are the requirements and what we really need to focus on. Some questions that we can ask here to clarify the requirements are, first of all, are we building the AI model itself or we are integrating with existing LLM models? And in most cases, we are just integrating with existing LLM models. We are not building the model ourselves. The other good question that you can ask here is, do we need streaming responses like word by word, or just wait until the complete response is available and send it over? And what this means, if you used these popular tools like ChatGPT, Cloud, Gemini, most of them use word by word method, which is they are streaming responses, and first of all, it makes it look faster because you get the first tokens before the next ones are being generated, and overall it provides a good user experience. That's why in our case we'll also be streaming responses for providing good user experience to the users. Next question is, we can discuss the scale, like what will be the expected scale that we need to handle. Of course, the initial idea is to just build and show that you're able to build this system to work like ChatGPT or other tools, but you need to also discuss what's the expected scale, and in the scaling phase, what are we looking at as numbers. And as of the last report, which is from January 2026, ChatGPT has around 800 to 900 million weekly active users. And these users are sending 2.5 billion prompts every day. That's a big write volume, but even more we will have read volume, as you will see later, and we'll need to design for both read and write availability. Another thing to clarify is whether users need to have accounts and conversation histories, or they just chat with the LLM, but then we don't need to store anything in the backend, because that would be a much easier variation where we just need to provide them the interface to chat with the LLM. But usually all of these tools have conversation history, and we will again need to support accounts for the users, private conversations for these users with the history so that they can access the previous chats. Another thing ChatGPT or Cloud or Gemini allow is to have shareable conversations. Once you chat with the LLM model, you can also share it. So another question is whether these need to be private only, where the user chats with LLM, or also shareable, because that's an extra functionality. And for now, to keep it simple, let's just say it's private conversations only. We don't need to provide any share functionalities or publishing on the web for sharing the link. A minor question we might have here is that whether we support multiple languages or not. And let's say we are just supporting English language for the LLM and overall for the platform. Another good question here can be about the tiers and overall rate limiting, which both are connected in this case. So how many tiers we will have? Is it like free and paid? And what are the rate limits in this case? Is it more for the paid users and less for the free users? And do we limit only on requests or on tokens? And for this case, we need to apply limits for both requests if users are sending a lot of requests in a short time, but also for tokens, because even when you upgrade, you have still some limited amount of tokens that you can use per period. And if your tokens expire, we need to let them know that they need to come back, let's say after 3 hours or 4 hours, when the tokens will reset for the account. Another thing to clarify is whether we support text only or images and files as well, because you can also attach files, you can ask it to generate images, but in this case, again, to keep it simple, we'll just go with text only. And lastly, we can ask whether we need to have some content moderation, because without this, usually LLMs can produce even dangerous responses for the users. Therefore, at least some basic content moderation is required in this case. Now that we've defined our requirements, let's start with what users actually see and interact with once they sign into one of these platforms like ChatGPT, let's say, because the most popular one out of them. It sometimes helps to start from the front-end interface design and overall front-end design to visualize what components do we have on the screen, and then based on that we'll design also the backend of the system. So if you take a look at something like ChatGPT, one of the most important parts here is the input box where you'll be asking your questions to the LLM. Another part is the conversation history, as we also clarified in the requirements, which is this left panel, this sidebar where you have your conversations. But you will notice that we have many functionalities other than that. So the thing we clarified and we are gonna build is the chat history, which is this part only. But other than that, ChatGPT and other tools nowadays have way more functionalities. They have things like projects, custom GPTs, OpenAI codecs, image generation, and much more stuff. But as we clarified in the requirements, we are only gonna focus on the chatting with LLM model and keeping the conversation history per user so that they can access it later. One important decision for the front end is that part which we talked about, which is whether we're gonna stream the responses or wait for the complete response to arrive. In case you don't get an answer, let's say from the interviewer on which one is the best choice, then you need to be also ready to present the pros and cons of each and then tell your decision on which one you're moving forward with. Let's start with the first option, which is waiting for the complete response to arrive. In this case, we'll be using simple HTTP post method to get the full response back. The problem is that users need to wait for the full response to be generated until they will see even the first print on the screen. And all this time will be just showing the loading spinner. And especially nowadays, this approach is very outdated to show just a spinner on the screen and let the user wait for something to arrive on the screen. Even if you don't show anything, you at least show the skeleton on what's loading, but we can't do that since we are waiting for the response and we don't know how big the response will be and what the structure of that is. Of course, we can show some skeleton that's close to the text that might be rendered, but still that's not a good user experience, as they have to wait from 10 to 30 seconds or sometimes even more if they are using the thinking models. And it will just feel slow for the user and they will get poor user experience in this case. The other approach is streaming responses, which is, first of all, we will open some persistent connection and we'll discuss how we will do this in the design phase. Then what we can do is, the way the LLMs work is they produce tokens, right, as responses. And we can start streaming tokens as they arrive. As soon as the first token arrives, we can already stream this back to the user, and user will start reading the response until the rest of the response is generated. And this way we are displaying words progressively, and users sees immediate progress instead of seeing some big loading spinner and waiting for the response. That also feels fast for the user and provides the user with great user experience. Of course, the only downside for this approach is that it will be a little bit challenging to implement compared to the first approach where you're just sending HTTP request and waiting for the response. But in this case, the trade-off is worth it because users will have much better experience in the second option. But how does this streaming actually work behind the scenes if we go with the second option, how we are going to implement it? We have two options to go with in this case, and the very first one that might came to your mind is WebSocket connection. This requires us to upgrade the protocol to WebSocket instead of HTTP, but it will provide us with bidirectional communication. WebSockets is generally useful for collaborative editing or typing indicators or anything that requires real-time connection, and you need to send back and forth data from server to client or from client to the server. The problem with WebSocket in this case is, first of all, it will be more complex to implement and it might add unnecessary overhead because we will keep many connections open, and most of the times, let's say we have the user who sends the request to the server, we will open this WebSocket connection and they will be switching tabs to do some other work, but we are still keeping this WebSocket connection open, of course with some timeout, but we are overwhelming the server for no reason if the user is not using the connection. This might be overkill for just streaming the AI responses. That's why the better alternative here, and the one that usually all major AI chat products now use, is the server-sent events and not WebSockets. One of the big advantages is that it still works over the standard HTTP, and this way server can start streaming tokens back to the user once they send us the initial prompt. The way it works is all major browsers have event source API built in, and it allows us to have one-way communication from the server to client to send events whenever they occur on the server. Also, auto reconnections here are handled automatically for us. Compared to WebSockets, this comes with way less overhead. We are just using the same HTTP protocol for streaming the responses. It's much simpler for debugging, and we don't have the overkill of WebSocket connection, and all major browsers have built-in support for this. Let's see how this can work on an example. Let's say user writes this simple short prompt in that input field, and we send this message from the browser to the server for the first time. This is where we will open that streaming connection and start streaming the tokens from the server to the client. For instance, as soon as the first token arrives, which is in this case, user was asking explain React hooks. So it will need to start with something like React hooks are functions that and the remaining parts. So the way it will look like is as soon as the first token arrives, like React, we immediately send it from the server to the browser, and the browser now displays this React word for the user to read until the next token arrives. And then server generates the next token, which is hooks. So we send these hooks over to the browser. Browser displays this for the user to read. Similarly, we stream all the remaining words and browser displays this one by one. And that is how it feels super fast for the user, because as soon as something arrives, we are immediately displaying it on the screen. and we don't let the user wait for the whole response to be ended until they can read anything. And once all the tokens are generated on the server side, this is where we stream the complete signal and show the complete response to the client and let them send the next request. So also during this time, this is where we disable the button of sending the next question because we are streaming responses. And if they want to cancel this to send a new request, they need to click on the cancel button or stop button there to stop the answers coming in, and that is when they can open a new connection and send a new query to the server. Now let's get into functional and non-functional requirements of the system. When it comes to building any systems, we usually need to clarify these two. And to simplify this for you, for functional requirements, you can think of this as what the system must do, meaning what are the features and functionalities of this system. And when it comes to non-functional requirements, we are answering how well it must perform in terms of availability, latency, scale, and so on. So let's start with functional requirements. First of all, we need to have user accounts so that we can save these conversations per user, right? That's why we need users to be able to register and authenticate to the system. After user is logged in, they need to also be able to create and manage conversations. So they need to be able to start a new chat. And after they have a conversation with the LLM, we need to store this in the database for retrieving later. Then they need to be able to send messages and receive the streamed responses by the LLM via servers and events. All of these conversations need to be stored with full history, including the user's prompts and the answers by the LLM. And we need to be able to retrieve all the past conversations and show them on this, let's say, left sidebar where all the user conversations are. And as we discussed, we'll be streaming responses token by token for the user to have a better experience on the platform. And we'll apply rate limiting for two scenarios. One is for the requests that will be coming in and one for tokens. And then we can modify these based on the tiers. We can increase the tokens for the plus tier or pro tier and have lower limits for the free tier. And we need to have some content moderation for harmful requests or responses by the AI. With these requirements, we define what the system must do and what are the functionalities, but then we need to also focus on how well it must perform and what are the standards we have here. So that is where we get into the non-functional requirements, and we can ask one of the questions here is about availability, how much we will need the system to be up and running. If we go with something like 99.9%, that means that we have maximum 43 minutes of downtime per month or something around 500 minutes downtime per year. And we don't just define these numbers for the sake of defining them. Later I'll show you how we also connect these non-functional requirements to the design that we have and make sure that it satisfies the non-functional requirements that we set in the beginning. But for now, let's just focus on these requirements. The second one is the latency, which is how soon the first token needs to arrive in our case, because that is the first time user receives the answer or at least portion of the answer from the LLM. And let's define this to be at least less than 2 seconds for the mini models. This doesn't mean the thinking models, in which case it might be a bit later because it needs time to process the request. But for the mini models, users wait no more than 2 seconds to receive the initial token. About scalability, we kind of touched on this. We will have 800 million weekly active users, or we can roughly make it to 200 million daily active users. And assuming we will have 10% concurrency for the peak times, we can expect to have 20 million concurrent conversations for the period. Another non-functional requirement is the consistency, which is, are we allowed to lose any data like the messages? And of course, in this case, we need to have zero message loss. All the messages by the user plus all the answers by the LLM need to be persisted to the database. It needs to be, of course, cost effective, because that's one of the major issues with running such systems and having your LLM models running on servers. We'll see why LLM APIs are expensive and what's the alternative for this. And for security, we need to provide end-to-end encryption, especially for private conversations. Once we set our performance targets, we can run these numbers to see what infrastructure we actually built, and we always start by estimating the capacity and storage. This is important because it will also drive the infrastructure decisions later on. So let's start from the traffic side, from the users. As with the latest report, the weekly active users were anywhere from 800 to 900 million weekly active users. Let's just also round it up to 1 billion, first of all, considering the future scale, and second, to make the calculations a bit easier for us. That comes down to around 200 million daily active users. And we know that we can expect anywhere around 2.5 billion messages per day by these users. If we divide this number by the amount of users we have, it comes down to around 12 or 13 messages per user per day. And 10% of these daily active users will be chatting concurrently in the peak times. That will come down to 20 million concurrent conversations that we need to handle. And for these messages, which is the average message per user, if we again assume during peak hours we will receive 10% or let's say 20% more of the requests from these users, it will come down to somewhere around 70,000 messages per second that we need to handle, which means 70,000 writes to the database by the user plus times 2, because also we will receive the response by the LLM and we'll be writing that also to the database. Next, let's calculate the storage for the conversations that we need to have. We need to have some average numbers here, either by assumptions or ask the interviewer if this is an interview situation. So let's say for the user message, the average question, if it's 100 characters, then it comes down to 100 bytes. And the average AI response is 500 characters, which is 500 bytes. Of course, these are averages. The message by the user might be much more complex, in which case we will receive more bytes for the message and more bytes for the response, but it can also be much simpler, like just a single question, and it will be much less in bytes and much less in the response. But for the average, this means that we will have 600 bytes trade per exchange, and one user, we calculated above, that will be sending 12 to 14 exchanges per day. We need to multiply these two together, which will come down to 7.5 kilobytes per user daily that will be storing. This includes both the message by the user plus the response by the AI. And with the scale that we have, which is 200 million daily active users, we need to multiply this by that average number, 7.5 kilobytes, and we'll be looking at 1.5 terabytes to be stored daily in the database. For data storage estimations, we at least look a year ahead, like what will happen in the next 12 months. So in this case, if we multiply that by 12, it will come down to 550 terabytes annually that we'll need to store in the database. This is the main thing that will consume memory in the database, but apart from that, we also have metadata storage, although it's not that huge, but we can still calculate this. For instance, we need to store the user profiles if you're gonna support registration and authentication. If you assume we're storing 1 kilobytes per user for the user profile data, which is the standard average, it will be this times the users we have, which is 1 billion, which will come down to 1 terabyte storage per user profile. For each conversation, we also store some lightweight information about this conversation. These are things like the title of that conversation, when it was created, when it was updated, is it pinned, is it archived, and so on. We can again take some average number here or just clarify this in the beginning. Let's say it's 500 bytes per conversation that we need to store. And if we multiply that by the amount of conversations we'll have annually, it comes down to 5 terabytes on average. And the total metadata size will be just 6 terabytes, which is not huge compared to what we have for the chat storage. But overall, the total will be around 550 terabytes that we need to store per year, which also shows that a single instance might not cut it and we might need distributed database here. But we'll come back to this when we get to the database design section. Two last things we need to calculate before getting to the high-level design. One is the connection overhead that we can expect for the 20 million users, which is the 10% of the total daily active users that will be concurrently chatting. This means that we'll need to handle 20 million concurrent connections with the servers, and each connection lasts somewhere around 10 to 30 seconds on average per the user chat, which means that we need infrastructure that can handle millions of long-lived connections, and we'll need distributed infrastructure for this. For the bandwidth requirements, when ChatGPT responds, the average AI response within the 20-second duration will be around 750 bytes, which is about 150 words. And it's streamed gradually over this 20-second period because we are streaming, let's say, one token per 2 seconds, as we clarified also in the requirements. For the 20 million concurrent requests, each of those will be streaming 750 bytes, which means if we multiply that by the 750, we'll get to 15 billion bytes, and this is streamed over the 20-second period. To convert this into throughput, we need to divide that 15 million by the 20 seconds, and that will give us the 750 megabyte per second throughput. Or we can convert it to gigabits, and it will be 6 gigabits per second that will be streaming. This is the standard unit for measuring network bandwidth. So we'll need 6 gigabits per second sustained throughput during the peak hours. Overall, these calculations show that a single server solution won't work, of course, in this case at ChatGPT's scale. So we need distributed systems and multi-region deployment if we need to scale it for the 200 million daily active users. Now that we know the scale we're dealing with, we can start designing the actual system that can handle it. And let's start simple with the high-level design for now. Before diving into costs and implementation details, let's map out the complete system architecture. We can break this down into 3 main layers. On the first layer, we will have the client where the users are accessing our platform. It's a front-end app and also possibly a mobile app accessing the servers. And this is where we also stream the server-send connections for real-time streaming. We'll also have the edge layer here where we'll send the static assets from the CDNs, and we'll also have the load balancer layer in front of it before accessing our API gateway. Then when it comes to the service layer, in front of everything we will have an API gateway. This is the entry point where we handle the SSL termination and also routing the requests like messages between the services that we have on the backend side. The core orchestrator here will be the message service for message processing and streaming back to the API gateway through server sent events. Since we need to also have users registered, we need to first of all have some auth service or user management service where we validate the authentication. Let's say if we use JWT tokens here, we need to validate that token in this auth service before processing the request. After that, we need to check the rate limits. For this, we can have a separate rate limiter service, which will track and enforce the request or token limits per user in some sort of session storage, like in Redis. Then for basic moderation, let's just not get into the details, but let's say we have some moderation service and we do some content check for the prompt that we received by the user and determine whether we allow responding to this query, or we might decide to not proceed after this step if it doesn't pass the moderation step. For all the CRUD operations for conversations and message history, we will have a conversation service. This will be responsible for retrieving the message conversations and also all the previous chats that the user had with the LLM model. And finally, we will use also some LLM gateway to not have the implementation in the message service. We will have a separate service that will be responsible for routing the requests to the clusters and handling the streaming responses. And on the data layer, we will still need to choose the database we will use in the database design. But let's just initially say that if we use some sort of SQL database, we will have some primary database and we might need replicas, and we'll discuss if we need some sharding as well here in the database design section. But at least we need to have replicas because in this case, even though we have 2.5 billion writes, the prompts that we are getting by the users, we are still dealing with more reads than writes for this system. The Redis cluster will be used mainly for the rate limits, for limiting based on either requests or limiting based on tokens. Since these conversations can get quite big, like one user might have more than 1000 previous chats with the LLM, and they usually don't need to access all these 1000. All they need is the recent 10 or 20 conversations to be active and available. So for the rest, which are not frequently accessed, we can store them in some sort of cold storage like in Azure Blob Storage, and this will be long-term archive for the old conversations. Also for the LLM gateway, this will be interacting with the GPU cluster, and when we get to the cost estimations, you'll see why we are using this over the API when it comes to accessing the LLM models. A few notes here about the cloud and infrastructure that is chosen. OpenAI usually uses multi-cloud setup to secure enough compute power and also avoid relying on single vendor. But still, Microsoft Azure is the lead provider for them. They have a massive long-term partnership with Microsoft. That's why when we get to also estimations, we'll be using usually Azure's costs for the services, but they still use other clouds like AWS because they also run some workloads on AWS's GPU clusters and specialized AI hardware. They also use Google Cloud Provider and Oracle, but the majority of the services are in Azure, and the second place is most likely AWS. When it comes to the order of load balancer and API gateway, in this case we place the load balancer in front of the traffic because it just distributes the TCP or HTTP connections across servers depending on the load balancer level, but it's usually a dumb version, so it doesn't have application logic on where to route the requests. That's why on the second layer we have API gateway. So once this has been routed to one of the API gateways, here we can read the URL like if it's /messages or /auth or any other route, and based on that it can redirect to the appropriate service in the microservices. And the response flows back through the same connection path. The HTTP connection that was sent, this stays open from the browser to load balancer to API gateway, and message service writes tokens to the response stream here. Then each of these tokens flows back to the user, and we are streaming the responses and displaying them one by one, the tokens on the screen. Now let's talk about the database design, and we'll need to first of all start from the scaling phase so that we can see what we are optimizing for. And based on that, we'll be able to map out the schema and relationship between the entities of the database. And this will enable us to make the database choice on what's the most optimal solution for this type of system. So first of all, let's start from the database scaling. Most engineers here might assume that ChatGPT runs on a sharded database, which actually isn't the case. If you check out the latest post made by OpenAI, you can actually see that OpenAI powers 800 million ChatGPT users currently with a single primary database, even though the load has grown by more than 10x in the last year alone. Their primary database still remains unsharded with a single primary instance serving all writes. And once we get to the database choice, you will also see why that is the most optimal solution for them. But one of the other components here is to consider whether this is a read-heavy system or write-heavy system. And if we link back to the initial requirements, we have 2.5 billion daily prompts that are sent by the users. So since all of these are write operations, right, because we are writing the message once they send the prompt, and then we are also writing the response that is coming back from the LLM. Here you might assume that this is a write-heavy system, but actually it isn't. It's roughly a 90% read-heavy system, while only 10% write system. And to understand why is that the case, it helps us to visualize the user flow and how the interaction happens on the system like ChatGPT. Let's say a user loads the account and wants to send a message to ask AI for something. So they click send, and then browser makes a request to post this message. So it comes to the API gateway, where we first of all route the request to the message service, and then message service handles the rest with other services. Like first of all, it validates the user, meaning it loads the user subscription quota info and how many tokens they have per their tier and how much of that is already consumed. Once the user is confirmed by the auth service, we need to also check the rate limits with the rate limiter. First of all, for the token usage on how many tokens they have left for their subscription, and second is also the request limits. And if the rate limiter allows to proceed, this is when we still need to check the content safety. So we need to do it with the moderation service. Moderation service will check this with the existing rules that we have and confirm that it is approved, and only then we can get the conversation context from the conversation service, and this will return us the recent messages. This is of course in case the chat is not new, so we need to also load the previous messages. But even if it's a new chat, then we still need to read the user's preferences, which ChatGPT also stores. If you know, there is this also memory feature, which remembers all the things that you prefer for reply messages, for anything, any context about you. We still also need to load this from the conversation service before being able to ask for it. And only after that we can send the prompt with the context about the user and about the chat history, if this is not a new chat, to the LLM service, LLM gateway. And this is where we will start streaming the tokens back to the message service, and then we will forward these tokens one by one via server send events to display them with typing effect on the client side. Once the generation is complete, this is where we will close the server send event connection, and this is only when we will first of all save the message that is sent by the AI and update the limit count in the rate limit service and overall for the database. And if we zoom out, you can see that most of these operations, like loading user account, loading subscription quota, loading conversation metadata, recent messages for the context about the user, checking rate limits, all of these are read operations. Whereas the write operations are only once in the beginning, where the message is written to the database by the user. And then next, when the message arrives by the LLM, this is also something we store in the database, and maybe also updating the limit count for the quota of the user. So even with this scale of 2.5 billion messages sent on average per day, we still have only around 10% write operations, while we have 90% read operations. And this is also one of the components that will dictate our database choice later on. Next, let's have a look at the schema of the database and how the entities are mapped together for this system. At least for the requirements that we discussed, which is having a conversation with LLM and then receiving the responses by this LLM, it's not that complicated, as you will see, at least for the core entities that we need to have. First of all, we need to have some users table or connection, depending on the type of database we will have here. The things that we need, first of all, is email for the user. This is how we identify them, apart from the ID that is generated in the database, which is the primary key. We'll have their password hash in case they logged in with email and password method. We need to have their tier, which is either it's the free tier or paid tier, or maybe there are free levels to tiers or more, and some more metadata like created it, updated it, and so on. But the important parts here is, first of all, the email, which is the identifier other than the ID that we have, and the tier, which is what we will look at. This is the field that we will check before making a request to the LLM. Because if it's a free account, let's say, and they run out of the tokens, then we need to check this first before allowing them accessing the LLM or blocking their access and telling the user to come back after some period or to upgrade to a better plan. Then these users can have conversations with AI. That is why we need to have some conversations entity where we have the ID of a conversation, the user ID, which refers to the user who created this conversation, a title, which will be again AI generated, created at, updated at, and some more metadata here. The important pieces is the user ID, which tells us which user this is connected to. And this is a one-to-many relationship. One user can have multiple conversations with AI. And for the conversation, we need to store the chat history, which is first of all messages by the user and messages by the AI. That's why we need to have some messages table or collection where we will store the message ID, the conversation ID on which conversation this belongs to. So here one conversation can have many messages inside. We also will store the role, which tells us whether this is a message by the user or this is a message by the AI or LLM. Each message will have a content, which is the text or the media files that are attached to it. But in the requirements, we clarified that we are designing for text only. So let's say this is a text field. And then we will have the token count, which is how many tokens did this message consume. This might be needed later for showing an invoice, or if you're using something like cursors model, where you show the conversation history and how many tokens each message consumed, you will need to also store the token count in the message. And then some more metadata, like when this message was created and so on. So that is how this looks like at a high level. And again, for a moment, if you assume we go with PostgreSQL, before getting to the decision, we will have a users table, which is this table here. When it comes to indexes, it makes sense for us to create an index like user's email on the users table email field, so that we can easily query the user by email here other than the ID. Then for the conversations table, we can create another index here on the user ID field and create it at with descending order. The reason for this is we will frequently need to fetch users' conversations and sort it by the recent. So they will have, let's say, 1,000 conversations once they use the platform a lot. But when loading the account, we only need to fetch, let's say, 20 or 10 to 20 conversations, which are the recent ones. That's why this index will help us to query this from the conversations table quickly. And other than that, we have the messages table. And for this one, we can also create an index to fetch messages in the conversation order. So we can create another index here on messages table on the conversation ID and the ones that are created at in ascending order. So this way, if we load a conversation and now we need to load the messages that belong to this conversation, we can load them in ascending order for the conversation, and these are indexed, which will help us to query them faster. Based on the database schema and also how the scaling phase will look like, let's now make the database choice on what we will use for the specific scenario where we have around 550 terabytes of data being stored per year. And then considering that we also have around 90% read-heavy operations, let's take a look at the 4 options we have available with their pros and cons and make a decision on which one makes sense here. And let's start with the traditional PostgreSQL database with a single primary database for writes and read replicas. This is what actually OpenAI uses, and let me walk you through the pros and cons here. First of all, we get the ACID transactions with the SQL, which is critical for a chat application, because as we also clarified in the beginning, we cannot lose any messages. All of the messages need to be persisted to the database, and if a user sends a message and the database crashes mid-write, that message must still either be fully saved or not saved at all. So we will get strong consistency in this case, which means that also in a conversation, all the messages will appear in the correct order. And this matters when you're looking at the conversation history. Of course, we can't have messages showing up out of sequence. The other important piece to it is that it's proven for the actual 200 million users with a single primary database, as OpenAI currently runs it. So this isn't just numbers in theory, it actually works currently on production. The other point which we also saw when mapping the entities is that the relationship model fits for the chat application like this. We have users who have conversations and conversations have messages, so it's a natural hierarchical relationship that SQL can handle very well. The good thing about this setup is that you can scale reads easily by just adding more replicas to it. And since the system is 90% read heavy, then we can easily scale that part by just adding more replicas. It's also battle tested at extreme scale. PostgreSQL has been around for decades, and every edge case, failure mode, or every performance optimization is well documented, and we know about all the edge cases. Now, of course, it has also cons to it, so let's talk about this. First of all, the single primary will become the bottleneck eventually for the write operations. Because with this setup, all the writes from every user around the world funnel through the same one database instance. And it comes down to around 30,000 writes per second for this scale. And that eventually might become a bottleneck for this system. You also need to offload write-heavy workloads to other systems. OpenAI, for instance, migrated their write-intensive operations to Azure's Cosmos DB because you can't just throw everything at the single primary database and expect it to work for this scale. And also at this step, it will require careful optimization, probably a separate team taking care of the PostgreSQL instance only, thinking about the query timeouts, index management, write batching, and more stuff like that. Now, what about the other option, which is using MongoDB? Because it's also the classic web scale choice. Let's see if this actually makes sense for a chat application like this. First of all, the pros of this is that it comes with built-in sharding. It was designed from the ground up to shard data across multiple servers, and the database handles the routing automatically for you. That might be something that will scale the writes, which we can't in a single primary database with PostgreSQL. Other than that, we also have the schema flexibility here because you're not locked into a rigid table structure. If you want to add a new field to messages, you don't need any migrations for that. You just need to start adding that new field for the future documents. And it's also good for write-heavy workloads because MongoDB's architecture handles high write throughput very well. But it has some major cons, which are the reasons why we don't go with MongoDB in this case. First of all, the consistency in MongoDB is eventual consistency, so it doesn't guarantee strong consistency by default. And yes, you get also the ACID properties in MongoDB for single document level, which means if you update a single document, the operation either fully succeeds or fully fails. But for multi-document transactions, although MongoDB added full ACID support since version 4, still the heavy use of multi-document transactions in MongoDB will hurt the performance a lot. And it doesn't work as good as it is in SQL databases. And for our specific case, you could have a situation where, let's say, message 5 appears before message 4 in the conversation history, and that will mess up the whole conversation for the user. It is also less mature for complex queries. If you want to run complex joins or aggregations, that is where the SQL's query planner is decades more sophisticated than MongoDB's. And the other point which I also touched on, which is the message order, is very critical for this system. You can't have messages out of order in the conversation. These combined are the reasons why you can't go with MongoDB for this case. Of course you can, but it's not the most efficient solution here. So if that's not a good solution here, let's also see what are the other options that we have. The other one is to go with a serverless PostgreSQL with Neon. This way you kind of get the best of both worlds by first of all getting a managed infrastructure, which means that you're not dealing with replication configuration or backup schedules or failover scripts. This all is handled automatically and your team focuses on building the product, not managing the database. And this isn't a PostgreSQL-like database, it's actual PostgreSQL, which means that every query, feature, or tool we know that works exactly the same here, and we are not learning a new system. Neon also follows the same high-level architecture pattern with a single primary for writes with a flexible number of read replicas for scaling the reads. And it achieves this by using a different replication model where all compute nodes read from shared storage and intentionally offers less low-level configurability. And this way you're trading manual tuning and operational control for a more automated and hands-on platform. The other good thing about this is that you get the automated scaling. The database scales up when you need it and scales down when you don't. So during peak hours, you get more compute, and during off hours, you might even scale down to zero. And you only pay for what you actually use for the platform. And with branching, you can also create instant database copies for testing. You can think of this like Git, but for databases. Let's say you want to test a risky migration. We can branch the production database, run the migration on this branch, and after we verify it works, then only we merge it back. And you can also set TTL branches, which expire after a set period. So you create a branch for testing, set it to expire in 24 hours, and you can forget about it because it cleans itself and saves compute costs. And storage here grows independently from your compute power, which means you're not paying for massive compute instances just because you have a lot of data stored there. And lastly, you can also spin up a branch for your staging environment or for your dev environment, and then you can test your changes here. After that, you will destroy the branch when you're done, and you're not paying to keep the staging database running 24/7. Of course, this has a couple of cons to it, which is, first of all, at this scale, you can't really rely on the scale to zero feature. So if you're talking about the 200 million daily active users, then of course you won't be benefiting from the scale to zero because you will always have users using the platform. There is also a small learning curve for the team because if all team members are used to traditional PostgreSQL operations, then they need to also learn concepts like compute storage separation, branch lifecycle management, scale to zero behavior, and more functionalities that Neon provides. And lastly, the infrastructure that OpenAI has currently is PostgreSQL on Azure, where a single instance can scale up to 128 virtual CPUs and 512 gigabytes of RAM. And Neon's current maximum compute size roughly comes down to 56 virtual CPUs and 224 gigabytes of RAM. With that being said, of course, these limits are not fixed and they can be increased as the platform evolves and as they get more users who are using this much compute power. And the last option that we have here is sharded PostgreSQL database. This might sound the obvious solution at the beginning when you hit the write limits, but it also has major downsides, which are the reasons why OpenAI didn't go with PostgreSQL sharded version. So let's start with the pros, which is you can distribute the write load across multiple primary databases, which solves the write bottleneck. Each shard can handle a subset of users if you decide to shard by users. So you can set 1 to 100 million users to write to shard 1 and 100 to 200 million users write to shard 2. This is genuinely better for write-heavy workloads. If you're running a system where the writes equal or exceed the reads, then sharding makes sense in that situation. But here are the cons that we have here, which is, first of all, it requires massive changes to hundreds of application endpoints, which is how it's stated by the OpenAI. This kind of change can potentially take you months, if not years of work, because every piece of code that touches the database needs to know which shard to route to. You need routing logic that looks at the user ID, hashes it, and figures out which shard to connect to, and every query has this overhead. So although it will solve the write bottleneck, it will also massively increase the complexity of the system. And you also need to handle distributed transactions across these shards if you decide to go with sharding, which is harder than with a single primary database. Considering the pros and cons of all these solutions, let's now see when to use Vault based on the stages of this system. So if we talk about the first stage where you have 0 to 5 million daily active users, you can start with Neon in this case because, First of all, you will get the managed infrastructure. It's the same architecture that OpenAI uses, which is single primary with auto-scaling replicas for reads, but it's also serverless, which means you can ship 10 times faster because you're not spending weeks configuring the replication and backup strategies. This is managed automatically. And you also get the instant database branches, which means you can easily test the migrations. In traditional PostgreSQL, spinning up a staging database can take you 20 minutes. With Neon, you can just branch in seconds. And it's also cost effective because you only pay for what you use in the beginning, which means you might actually benefit from the scale to zero feature at this stage if you have no users using the application for some time. So that's the fastest path to market for the stage 1. Now, what if you're in the stage 2 where you have 5 to 100 million daily active users? If you have started with Neon, you can still stay on it because as the traffic grows, it will automatically add read replicas and you don't need to manually scale your database as you need more replicas for the system. At this second stage, you need to start identifying which workloads are write heavy and need to be offloaded from the system on something like Cosmos DB on Azure or other solutions to not overwhelm your single primary database if you go with non-sharded version. But everything else that is on the primary database is still handled automatically in the managed infrastructure. And you don't have to configure everything manually, which means it can be a smaller team working on the core functionalities for the application. Now, what if you get to stage 3, which is 100 to 200 million daily active users? This is where if you need full absolute control, you can migrate to self-managed PostgreSQL on Azure or AWS with one primary for writes and 20 to 50 read replicas. This way you will offload the write-heavy workloads to separate sharded systems like Cosmos DB, just like OpenAI does. But this comes with a trade-off of having more complexity and you have to manage everything yourself. So if a managed infrastructure is still worth more for your team to save some efforts, then you can stay on the solution you have until you hit the maximum compute size here, which is the 56 compute units that you can have and 224 gigabytes of RAM. And at that stage, maybe these limits have already increased and you can still stay on the solution you went with. Now, if we talk about the stage 4, which is 200 million plus daily active users, this is where at some point you might need to actually shard the primary database and go with a sharded PostgreSQL approach. The thing is that up to this point, which is 800 million weekly active users on OpenAI, they still haven't needed to do this yet. So for 99% of companies, even those building the next competitor for ChatGPT, they might not hit this stage and not need the sharded PostgreSQL solution. One thing you can learn from this stage is you don't need to over-engineer early. As we can see, OpenAI still uses single primary database plus read replicas that work at scale far beyond what anyone thought possible. And they went from 0 to 800 million users without sharding till this point. They are using only one primary database and around 50 replicas for read operations. With our database architecture decided, now we can also define how clients will interact with the system. And for that, we need to move on to the API design and think about what will be the endpoints and how will we expose these functionalities to the client. We'll go with a simple RESTful architecture here because there is no specific need for having GraphQL for any of these services. Let's start with the authentication flow, which is handled by the auth service. This is where users will log in by providing credentials, and then we need to return them the authentication token if it's token-based authentication. These are some of the endpoints that we will expose. The first one is for registration, where we will send a request to /auth/register. This is for creating a new user account. And in the body, we will have generic things like the email of the user, the password that they set, and any other details that we require from the users. In the response, we will include the token, like the JWT token in this case, and this can of course include user details like the user email or user ID, but we will need to return some more data from the user, which we'll do separately in the response body. Similarly, we will have also a login route, which will be for users who are already registered. Here we will expect the email and the password if it's a basic like email password authentication, or they might be signed in through Google or through some other provider. And we will return the token similar to the registration and any user details that we need, like the user account tier, whether they are on a free tier or paid tier, and any more details that we need for the front end. And of course the logout route, which is just an empty request to log out the user. The next part is conversations, which is handled with the conversation service, but through the API gateway. This is where we want to list the conversations, like the left sidebar panel where we had the past conversations for the user. We need to fetch these user conversations from the conversation service, and that in its turn will request it from the database. These are the most important endpoints we will have here. We will first of all have the get endpoint for listing the conversations. In the request, we will always provide the token for authentication, and the response will look something like this, where we list the conversations as an array, and each conversation is one object with all the metadata needed, like the title of the conversation, when it was last updated, a preview when we hover on them, and anything else that we need for displaying this on the front end. And from here, users can click on one of these conversations to open it. And that's where we need to have another endpoint for conversations / ID of a specific conversation. And here we will return more data with all the messages that's included from user and from the LLM. So the response will contain the conversation, the ID title, which is also included in the list conversations endpoint. But here we will have the messages. And this is where we will have the content, like what was the query from the user, and also the role who this message was sent by. And if it's sent by the assistant or AI model, then we will have the different role here and the content on what was the response for that question. This is also one of the reasons why we have around like 90% or even more reads in this type of systems like ChatGPT, where we have only 10% writes. Although you might assume that if we have 2.5 billion prompts per day, which are writes, right? And then for each prompt, we are also storing the response, which is times 2. But actually, that is still a smaller portion compared to the reads that we will be doing from the database. Because for each user prompt, we need to load the user account, we need to load the subscription and quota info, we need to then load the conversation metadata, and then also the actual messages that we stir per conversation. We need to also check the rate limits for tokens and requests, maybe also load feature flags and other stuff. And only the actual message that is sent by the user and the response that is sent by the AI, these are the only things that we write to the database, which in comparison is a smaller portion compared to the read operations. That's where we will also have the post conversations endpoint, where we store the conversation once it's started with the LLM, so that we can retrieve this later from the database. And we will also provide a delete functionality with the specific ID of the conversation. If user wants to delete the chat, they can just click on delete from the left panel, and we make a request to remove this from the database. And the last part is the actual messaging and also streaming the responses for messages when user sends a query, a prompt to the LLM, how we then stream these tokens and how we use the server send events to send tokens and events until the full response is ready. So this is the primary endpoint for that, which is post to conversations / the ID of the conversation where we're writing the message, and then to the messages. This is where we post a message, like user asks to explain React hooks, and then LLM starts to process the response. For that, we will open the stream to be able to send and stream these events from the backend to the frontend. And as soon as the first token arrives, we send the first event where the content is React, let's say. That's the first word that we got back from the LLM. Then this LLM processes the next part and it gives us the next token, which is hooks. And then the third token is R and so on. So we are sending these one by one to the front end. And on the front end app, we are displaying the words one by one, which makes it feel faster for the user and provides a better user experience. And if you wonder how this might look like on the front end side, let's say we're using React for an example for the front end. We can either use the native event source API or the event source library, which comes with more functionalities. And this is how a sending message might look like. We will need the conversation ID where we're sending the message and the actual message that we're posting. This is where we will make the request to that API where the message service will accept the message and start processing it. Of course, it will include the authentication method. And in the body, we will send this message that is sent by the user. This is where we will establish the connection between server and client. And then from this point, we create a new event source and we start the streaming process from the backend to the frontend. We can now attach event listener for the event source. And whenever a new token arrives, we get that token and then we append it to the message, which will display it on the screen for the user. Also, during the streaming, this is where we will disable the button for the user so that they cannot send a new query. They need to either stop the process or they need to wait until it's done to be able to send new messages. And then once the full message is processed, we will mark the message as complete. And then this is where we will enable that button again so that they can ask follow-up questions to the LLM. Let's also take a look at the rate limiter service and how we will overall apply the rate limiting. Modern LLMs usually limit on tokens and not just requests because you can send one request, but it can be a very huge prompt and it can include a lot of, let's say, code attached to it, and that will make the LLM to use more compute power for responding to your message than 10 average messages from another user. That's why we need to limit here for both token and also for the requests. For instance, in the first scenario, user might send one large request and a lot of code attached to it. The request count here is 1, so which means that it won't be rate limited if we only applied this for the requests, but it will consume massive tokens and a lot of compute power to be able to reply to this user's message. And if we don't apply token limits, then the price that they pay, which is whatever, like $20 per user, it will quickly outgrow the infrastructure costs that you have for running these LLMs. On the other hand, user might send many tiny messages like explain React hooks or generate a sort function or anything like that. In this case, it will be higher request volume. They might send like 100 tiny messages, will be low token count. So we still need to also have limits on the requests, otherwise they might start spamming and sending too many messages for the short period of time. So we can go with 2-tier limiting, and this will also help us for having 2 tiers for the users, like free tier and paid tier. And doesn't matter how much it is, let's say $20 for the user per month. And these numbers, of course, are variables. So for free tier, for instance, it can be 25 requests per day can be sent by the user, and then it resets on the next day. And it can be 50,000 tokens per day that you can use. So whichever runs out first, we will notify the user about it. And then they have 2 options. They either come back tomorrow or they upgrade to the paid tier. And for the paid tier, we can have higher limits. For example, it can be 500 requests per day, and it can be 2 million tokens per day instead of 50,000. And these are variables again, so you can change this depending on the system and how many requests you want to allow. But the idea is to have 2 tiers or more tiers if you have more payment plans. So for instance, this is how on cloud you have the free tier. Then you have the pro tier, which is 20. Then you have the max tier, which is starting from 100. And you can easily spend 200, 300 if you're constantly using the LLM and you need higher rate limits and higher token limits. This is how the implementation of that might look like. We will have some function in the backend for rate limit service, like check rate limit, and we will check it based on the user. For that, we need the user ID, and we need also their tier, whether they are on a free tier or on a paid tier. Based on the user ID, we will create the request key and then the token key, and these are what we will take a look at to compare if they are out of limits or not. Here we need to use some storage. This is where we mentioned Redis, for instance, that we can use for storing the limits and how much they consumed so far. We will check what's the request usage and token usage from the Redis store. And then we'll get the limits. These are the variables like how many requests they can do per tier and how many tokens they have per tier. And after we have how much they consumed and what's the limit, we can just check if they are within the request limit and if they are within the token limit. And if both are fine, we will allow these to be processed. Otherwise, we will let the user know that they are out of tokens or out of requests. Let's also calculate the costs, or at least roughly we need to be able to estimate what will be the cost for running this. Of course, these are very rough estimates. We can't possibly detect how much exactly OpenAI is paying or other companies are paying for their infrastructure, but we can roughly calculate each component, like how much they pay for GPU infrastructure if we have the amount of users and we have the amount of average prompts per day. We can calculate how much it's spent for the networking, for bandwidth, for the data layer and operations. So that's what we will do here. I will briefly mention each component, but for the exact calculations, you can pause and see what we have included in each part. So first we need to estimate the LLM API costs if we are using these through APIs. Because if we are building just a wrapper around OpenAI's API, like many startups do, then the pricing for, let's say, the mini models is still pretty high through API. And the daily cost for us will be around $5 million for this amount of users. And that will end up being a lot for the monthly costs. But the thing is that OpenAI Cloud and others, they have their own LLM models and hence they are not consuming it through API and with these massive costs that they have on the API. Instead, they deploy their models on their own GPU clusters and then the model serves directly, not through API. You can access it through the cluster. And basically the price that you pay here is the price per token for the compute time, not the API pricing that they have for the other users. The next very big component is the GPU infrastructure. Here we need to first calculate how much we will utilize from the GPUs and then we can also apply smart batching, but overall for 200 million daily active users, this comes down to $52 million per month. This is one of the biggest components for running the infrastructure. The other thing is the database where we decided to go with PostgreSQL, and even if it's a single primary and read replicas, so we are not sharding the database, it will still round up to us having 20 replicas minimum for the amount of traffic that we have. And for the storage that we calculated, which is 550 terabytes, let's just round it up to 600 terabytes. For running these with 20 replicas, that will come down to $138,000 per month. Of course, this is very tiny compared to the GPU infrastructure that we have to pay for. The other components are API servers, the next part, which is how many API servers we need to have. And as we discussed also in the high-level design, OpenAI uses multi-cloud strategy, but primarily runs on Microsoft Azure. So we will use the numbers from Microsoft Azure pricing. For the peak concurrent sessions, which will have 20 million users chatting with the LLM models, it means we'll have 2,500 concurrent connections. And the servers needed for this is the users divided by the concurrent sessions, which will be 8,000 servers. If we also distribute this across 6 regions, that roughly comes down to 1,300 servers per region. And that will end up being $4.6 million per month. Most of the other components are tiny compared to the big components that we discussed. For instance, for load balancers, it will be 75,000 per month. And again, for each section, you can pause and see how the calculations go. And for the Redis store, we'll have around $130,000 per month. Bandwidth is one of the biggest ones again. This is why also we calculated the bandwidth in the storage estimation section. So if you also calculate how much that will cost you for having this much bandwidth, it will be around almost $1 million per month. And apart from that, we'll have again small costs compared to overall what we had here, like 15,000 for the content moderation, for monitoring and logging around $150,000 per month, and for the CDS we'll pay around 75,000 per month. So the single biggest component here for the cost is the GPU infrastructure. After that, it's the compute of the servers that we need to have, and then the rest is usually small compared to what we have for the biggest component here. And the total comes down to $58 million per month. With that, we covered all of the functional requirements that we set at the beginning. But if you remember, we also had non-functional requirements, things like 99.9% availability, first token under 2 seconds, scalability to 200 million users, consistency, cost efficiency, and security. We need to also be able in interviews and also in production systems to map out these first non-functional requirements back to the architectural decisions we made and also show how our system achieves these numbers and this level of non-functional requirements. That's what we need to do next. We need to map all these non-functional requirements back to the design decisions that we made during this system and also show how our system scales to 200 million users and above with the multi-region setup. The rest of this breakdown is exclusively for the members in my mentorship program. If you want to be part of it, master system design, to be able to design systems like this from scratch and land senior offers, then check out the first link in the description to see if you qualify for that. And I recommend you also watch this video next, which is a full breakdown on most of the concepts that I used by designing this system, more in depth, like database sharding, database replication, API design, and more.